Hello everyone, welcome back to Mind Maths with Amna. In today's lesson, I'm just continuing the DSGE model, which we previously started. Actually, this is a typo here. This is part 3. Um, we've already done, in part 1, I covered a monetary innovation shock. In part 2, I covered a government spending shock. And now in part 3 of this, I'm going to cover a technological shock. So basically a supply side shock. You could think of this as a shock in the Phillips curve or the aggregate supply curve. Okay, again the procedure is similar to the what we've been doing before. Um, as a step 1, we're going to identify the endogenous variables. In this case, we have output and inflation and interest rate as well. But because I'm going to actually substitute the Taylor rule into the IS curve, and I'm going to be left with a 2 by 2 system with only two endogenous variables. Therefore, I don't need to state the interest rate as an endogenous variable right now, even though it is. Okay. And the shock this time is on technology. So it has to follow an AR1 process. Okay. So which means that AT will be equals to rho AT minus 1 plus ET, where ET is white noise, and rho is just the degree of perpetuity. If rho is equals to 1, it's a permanent shock, everlasting kind of. And if rho is equals to 0, it's a short term temporary shock. Okay, so moving on, it's actually the equation becomes much easier if we make certain assumptions. We can safely assume that there is no monetary innovation shock. We can assume that there is no inflation shock. We can assume that there is no output shock. And for simplicity, let's assume that there is no government spending growth, like there's no change in government spending. Please do remember that all these small variables actually are in logs. This is actually a small y. So therefore, when I say government spending is 0, it doesn't mean that the level of government spending is 0. It just tells you that it's not changing. So there's no growth in it, but there is some level of government spending in the economy. Okay, so these are the assumptions. So first, let's put let's first simplify these equations. So let's simplify these first by putting in these assumptions. Okay, what will this become? This error goes away. Since g is equals to 0, all of this disappears. That's nice. This goes away. This goes away. This goes away. Yeah, and we're left with this. This is quite compact and much easier to manage. And now I'm going to put the Taylor rule into the IS equation. And then we'll get a 2 by 2 system. So this is my IS equation. And again, I'm going to substitute the Taylor rule here. This was my Taylor rule. It's in a central bank that targets both the output and inflation level. Remember, if there's a demand shock, there's going to be no trade-off between output and inflation. And when there's a supply shock, there will be a trade-off between output and inflation because of this Taylor rule. Okay, so now these are the two equations that we have to deal with. So we are going to write the trial solutions and substitute them into equation 1 and 2. So what are the trial solutions? The trial solution, because we are again looking for a multiplier, so it has to be the derivative should give us that constant. Okay, so let's suppose y is equals to b a t. The reason why this was the trial solution is because I can conveniently see the change in output after changing technology is the constant b. Okay, similarly, the trial solution for inflation can be made c into at, and this helps us identify how inflation will change after a shock in technology. Okay, moving on. Uh, Again, also one thing to remember is that since AT is an AR1 process, so it's rho AT minus 1 plus ET, and therefore whenever we have I don't think we're just going to substitute that here, and that's not gonna, okay, let's find out the value of this and this. Okay, so expected value at time um, t of a future inflation is basically the expected value of c a t plus 1, and the c goes outside and we have at plus 1. If I lag this one period forward, at plus 1 is equals to rho at plus et, and if I take the expected value of the above expression, I'll just take it over here. If I take the expected value at time t of at plus 1, because the time period is same, therefore I don't need the expected sign, and this becomes a 0 because that's white noise with mean 0. So therefore this becomes a c a rho a t. Similarly, the expected value of y in the future period is expected value of b a t plus 1, which is going to become a b rho a t. Now we have all our information. Let's plug the trial solutions into our main equations. So plug the trial solutions into 1 and 2 and solve for the multipliers. Solve for b and c. Okay, let's do it. This was my first equation. I'll put it right here. Okay, let's start. Bismillah. Y was a b a t. This was a b rho a t minus gamma inverse of sigma coefficient of output into b a t plus coefficient of inflation into c a t minus this was a c rho a t. I think that's it. Okay, so all these ATs get cancelled out, and we can take B and C in on the left hand side. So I get a B over here, B rho into B minus gamma inverse of sigma coefficient of output into B And then we have a minus gamma inverse of sigma coefficient of inflation into C, and then we'll get a plus, and this there's a row here, C. Okay, so what do we have with B? It's a 1 minus a row plus gamma inverse of this. Okay, these are all the coefficients with B. And with C, I'll have a gamma, this expression, okay, and with inflation, and this is going to just change signs and C. And there's no coefficient actually over here. So that's my first trial solution done, and the second is actually going to be as per usual easier to find. So let's just hurry on with this. This is going to be C A T plus X C rho rho A T plus whatever the sign is, B A T minus whatever this is, and AT remains here, cancels out, AT disappears, and I can take everything on the left hand side. So this expression would be plus 1 minus rho X into C, and minus this stays here. So this is the second equation, and now we can put these together and convert into matrix form. So let's convert into matrix form. Okay, moving forward, I should actually have the pages out ready first. 1 minus rho plus gamma inverse of sigma coefficient of output minus this here, and this expression minus rho 1 minus rho X, and we get a B here and a C here. We are lucky to get a 0 in our B column vector. Yeah, let's just use the Cramer's rule again instead of taking the inverse. This is a AX is equals to B system. We can actually take the inverse and just multiply it by B, but I usually prefer the Cramer's rule. So let's take the determinant of this matrix. We'll have this expression multiplied by this minus, and because it already has a negative sign, this is going to become a positive, multiplied by this. Okay. As you can see, this is positive since the inflation, the coefficient of inflation is definitely going to be greater than 1, and this is going to be less than 1. So this is actually greater than 0 if and only if if 1 is greater than rho minus this, which actually holds true, and 1 is also greater than rho into X, and the inflation coefficient is greater than rho, which is also true. And besides that, we already know that all of these are positive numbers. So the determinant is positive. Let's find out the value of B. We're going to replace the first column with B. So it's going to be a 0 and minus 3 here. And this remains the same because B was the first entry. So we are going to change the first column. And this determinant will get divided as per the Kramer's rule by the determinant of the whole matrix. So we have a positive answer here. So what was B? I think it was a change in output. Let me see what was B actually. B was a change, yeah, told us about a change in output because of a. So it says that if there is a positive shock in technology, which basically shifts the long run aggregate supply curve to the right, then as a result, it should cut the aggregate demand curve on a lower level of inflation and higher level of output. Just in case if anybody's having a trouble visualizing this, this is the aggregate demand and we're moving from point A to point B. This is output, this is inflation. Okay, let's find out. Hopefully the value of C is going to be negative, otherwise this is going to be very embarrassing for me. Okay, the first column now remains the same, so this remains the same. Copy and paste, and the second column now gets replaced by the column B. So we have a 0 minus this over here over the determinant. Oh, nice, beautiful. This is why I love mathematics, because when you do get the right answer, it's just quite frankly very thrilling for a person like me, because maybe I'm a nerd, but this is quite thrilling. We actually did end up with a negative number, so I'm quite happy right now. Okay, so we have a negative C as because of this negative sign here. So it shows that hence we can conclude that a rise in productivity as given by a positive shock to A leads to lower inflation. So it decreases the inflation rate. And what about the interest rate? Again, the interest rate was given by this Taylor rule. And I think the answer is going to be ambiguous because both of these things are going in the opposite direction. But let's write it down first. So we have the B here, and we have inflation, and we have C here. Yeah, this is going to be a positive number, this is going to be a negative number. So the overall impact is ambiguous, and it depends on the how ISLM curves have shifted, and which impact outweighs the other one. Anyhow, so this brings about an end to the DSGE series. There were 3 classes in these series. There we did a shock to technology, shock to government spending, and shock to monetary policy. If you get a question in which the shock is given to any other variable, you just have to follow the same procedure and you'll get the right answer. And this is enough for today. Take care, and I'll see you in the next lesson. Bye.